Hi there. I'm Geoffrey, product manager for C and C++ ecosystem at Sonar. And today I would like to talk to you about rules, standards, and AI, what coding standards really do and why they still matter. So just a few words about myself so that you can better understand the angle of this talk, right? I started probably like 7 years ago at Sonar as a developer in the C++ analyzer development team. And since then, I transitioned to being the product manager for the C and C++ ecosystem. So back in my developer days here, I was deeply involved in crafting rules, implementing them in all the details. Right now, as a product manager, of course, I don't get that much into the details, but I still deal with rules at a higher level, let's say. And also, I got to dive into coding standards. And we're going to talk about this. As I said, we're going to talk about standards. Standards is really like a broad word I've used to put all sorts of good practices together. So it really ranges from things like OWASP Top 10, which are really high-level awareness standards, to really hard requirement standards like MISRA. For instance, there's no way that you're going to ship any critical automotive software these days without the MISRA badge on it. Or it's going to be very difficult for you to pass some requirements without being able to demonstrate some OWASP ASVS compliance. And this is the sort of things that we are dealing here at the highest level. But concretely, when it comes to your code and what developers see when they use our product, they see the result of rules that are really small individual atomic checks. And we'll have a look at the link between these two. So what we're going to do, we're going to start with standards and see that they have purpose and philosophies. We're going to go down to at the rule level and to really understand that rules are tools serving standards, but they are not truth. And then we're going to have a look at AI, because AI now is everywhere. AI is most certainly into the coding business, and we need to understand what it changes. And spoiler alert, it doesn't change the fundamentals. So let's get started with this very homemade chart where I put some of the most famous, let's say, coding guidelines. So on the left side, you would have like very abstract guidelines that are not really strict in their level of prescription. To the extreme right, you will see mostly things that are very prescriptive on what problems you are tackling, how you should tackle them or resolve them, like MISRA, which is something very hands-on in the code with very strict rules that you need to follow. On the vertical axis, you will have at the bottom things that are really mostly dealing with code and nothing else. And at the top, you will have standards that really specify the entire full system lifecycle management. And it is very important to understand that when you consider all these standards, there are cost trade-offs to be made if you want to follow them somehow. If you want to solve a problem, there are a variety of solutions. And depending on the cost you're ready to put, you will have different level of solutions, let's say. So for instance, constraints. Of course, you can code quick and dirty, but most likely you will introduce bug, and it's not good for the safety critical application and this sort of stuff. So you want here, there is a first level of trade-off. You can't be that fast. You need to do things properly to be sure they are done properly. There are trade-offs on expertise. You will have additional processes, additional audit, and these sort of things. Are you ready to embark into this and to support the cost that comes with it? There is also the tooling. For instance, if you consider security, you have static analysis, dynamic analysis, software composure analysis, real-time application, self-protection, and these sort of things, all sort of things that come to a cost, and that can also harm developers' velocity. So that's, let's say, the standard spectrum. I would like you to now, we're going to move on to a few examples to see that in action somehow. So the first one is OWASP ASVS, which targets web application security. The purpose of the standard was merely to stop the guessing game in security verification. Because it was not standardized before, it used to be difficult to understand what needs to be checked, by whom, what, all these sort of things. So the philosophy is really to make security testable and contractual. So the content of this standard is mostly 286 testable requirements, various categories and levels. And this comes with really 3 functions, let's call it this way. So first, it's a metric. That's very important because checks have different levels. You can say, when we develop our application, we are conformed to ASVS level 2. That actually means something specific. It's also a blueprint. All the security requirement to build into the code is specified in these testable requirements. And it's also a contract, and that's a very powerful feature of this, which is basically you can use this to subcontract software development. You can say, I would like you to develop this application while being conformed to ASVS level 2. And that's a very powerful feature of standards in general. Another standard I wanted to take as an example is MISRA. So MISRA, so we're going to focus on the C++ version of MISRA. There are other versions, but for the example, that's fine. So MISRA was born in the automotive industry with the need of really streamlining what it means to have safety critical code. And it also became a de facto standard in functional safety more broadly. And the purpose of MISRA C++ 2023 is to define a safe subset of C++ 17. C++ is a very complex language. C++ 17 is a version of it which is very complex with many features. And a group of experts decided that it's much better to restrict it to a safe subset of functionalities that you're able to use in your code. So they came up with 179 very detailed specified guidelines plus a compliance procedure, detailed one. And all these guidelines are classified in 2 categories. They were all made with a static check in mind. There are decidable rules. The decidable rules, basically, it is mathematically demonstrated, basically, that you can implement a perfect check for such a rule. So tools vendor will not really differ much in the quality of these findings. For undecidable rules, that's a different game. There's not many rules undecidable because they're undecidable, but they tend to cover very critical bugs. So there you want to have something good. But little spoiler, in my own experience, after these years at Sonar, I would say the best bugs are the ones that you never wrote. So basically, it's really great to have good bug detection capabilities, but the first thing you should focus on is to never write bugs. It's a bit like if you have a car, of course, you want to have the safety belt. Of course, you want to have an airbag. But of course, the first thing you should do is to focus on being a good driver. So that's the same with code, basically. You can check out what we've been doing about MISRA C++ compliance recently if you want there. So the last one, the last standard I want to talk about is Sonar Way. And people that know a bit our product will say, hey, wait, it's not a standard. Yeah, it's not exactly a standard. I acknowledge that, but it really fulfills the same role somehow. So it targets mostly all industries. The purpose is to be sure that your code remains an asset, secure, reliable, and maintainable. And the philosophy there is really like try to shift left and be actionable and educate your developer to doing so, right? So basically, what is the content of Sonar Way? It's a set of default rules that we enable for each and every single language. Let's say for the bigger languages like C++, Java, or Python, this is between 250 and 600 rules by default for this language that will take care of all the aspects of the code that I've named before. So I think this is not standardized, so it can be used as the previous standards, as we said, but it can be used for internal purpose, and that is being used by our customers for this internal purpose. So now I would like to zoom in a little bit on rules, as I said we would do. We will use here 3 standards, 2 of which I've already mentioned. So first, we need to understand that, for instance, in Sonar, we can either write original rules, our expert will write rules as they see fit, or we can also adapt other rules from external standards and implement them as required by some standards so that our customers can use these standards. Any of such rules can map to either standard to whatever standard if they fulfill some part of requirements of these standards. It is what I would like you to understand, to take away from this slide, it is that rules solve a problem and they have a philosophy, mostly inherited from some coding standards out there. And we will take these three examples. So first, MISRA is focusing on safety criticality and aims at defining a safe language of the subset. And things that you will see out of MISRA are things like, oh, you should not use this or you should not use that. Then it's your job to try to fix it, but you need to fix it or to justify that you did not fix it. CERT is another standard that's trying to go around vulnerabilities with a philosophy that's very much defensive. So for instance, it will often tell you, oh, you should make sure that this is validated or that is validated in your code. So it will give you plenty of issues in your code with various levels of priorities, and you're free to fix whatever you're able to fix there. Then there is Sonar. There is our own rule set at Sonar. So it's about software and code health in general. It is the philosophy is about shifting left, as I said already, being actionable and educate developers. So the sort of issue that you would get out of Sonar rules is, oh, this thing is dangerous because of that reason. Please do it this other way, please. So this is very actionable. So it has various quality. You understand the problem. You understand the source of the problem, and you understand what you need to do to fix it. This is, as I said in the philosophy part, very actionable. And we have this workflow called Clean as you code to help you actually applying this with all the new code that you put to your application, so that over time your entire code base gets clean. So we're going to have just a quick look at a concrete example for all this to sound a bit less theoretical. So this is a little bit of C++ code. I know everyone is not familiar with it, but it's going to be quite simple. So there is a function that takes a pointer to a const integer, and this is casted with a certain sort of cast, this parenthesis around unsigned integer. And this cast has problems. I will explain this. So basically, it can create unexpected consequences in your code. So MISRA says that this functionality, casting with a C cast, is totally banned. You must use named cast, as I wrote them in the comments. You have static cast, dynamic cast, const cast, reinterpret cast, that allows you to state your intent. So there's no exception. This is banned by MISRA rule. CERT has a different angle. CERT says, oh, we are aware of a few occurrences in specific cases in CCast of dangerous cases. Please check that it's not one of these cases, but the rest of the time, we don't care you using this C-style cast. Then finally, we have the Sonar rule. The Sonar rule actually discourages. It's not as hard as MISRA rule that totally ban this practice. At Sonar, we just say, oh, look, this is not a good idea because you're really hiding your intent here. It hurts readability of the code and then can be misleading. So you should not do that, and we have other ways for you to do it. So now the final part of this talk is about, so I've been talking about standards, I've been talking about rules, and now we all know that the world of development is changing big time because of AI. What does it change here? So are coding standards still useful? Well, yes, they are. Why are they? Because mostly LLMs write code that looks a lot like human written code. So that's the first reason. They will mostly do the same blunder as we can do as human beings. So all these parts that were crafted in the standards and in the rules to spot these blunders, yes, they will still work. So, and are they still enough? All these standards and these rules. For the code itself, largely, yes, but not for the full picture. So the code itself, we've run a very interesting study that you can see here. It's called the coding personalities of leading LLMs. What we noticed is basically that LLMs write code a bit like human beings. They do the same sort of mistakes in various proportion, depending on which LLM you're using. So from that perspective, one more time, yes, All this is still largely enough from that perspective. But there is a but. AI is also introducing new risks that we're going to have a look to just right now. So the risk that AI is introducing, the first one is AI as a code writer. So AI is not really inventing a new sort of mistake, but is doing these sort of mistakes much more often than a human programmer would do it. The first one is logical and flow, which is like the happy path coding, like it's like when you only consider the main use case of your program and you forget about edge cases, error handling and all that stuff. AI tends to do that a lot. Dependencies, slope squatting. This is an interesting one. Actually, AIs will invent some packages that don't actually exist just because that would sort of make sense they exist. And so some studies suggest that up to 20% of introduced packages in some code by AI does not actually exist. But if someone is smart enough to actually implement this package that does not exist yet, they could sort of inject your code inside your code, their code inside your code. So that's a big risk, and it's called slope squatting. There's also maintainability issues with AI, code churn, copy paste, big blocks. All people that have been using AI to write code, they've been around this, you know this. This is not really good for maintainability of your code. And finally, there is architecture. Basically, AI is mostly generated, isolated snippets of code without a bigger understanding of your code, and is leading to architectural issues. And by the way, you can have a look because we also have an upcoming solution for architectural issues. And the second category of big risk that AI is introducing is AI is just simply a new software subsystem, a big one, a very big one that is being used more and more. And so it's introducing ways to do things badly, unsafe ways. It's introducing bad things that you should not do. And for that, there are new standards to tackle these problems, like OWASP Top 10 for LLM applications. So I would like now to wrap up this talk. So first point, I would like you to remember, coding standards have purpose and philosophies. That's important. It translates to rules. Second point, a rule is a tool to tackle a problem. It's not a single source of truth. If you're being said that something is a single source of truth, about rules, there is something fishy there. AI generates big amounts of code. Yes, but it's mostly similar to human code. So most of standards and rules are still valid for this code. And finally, AI introduces new risks. And these new risks are being tackled or are on the way to being tackled by existing standards and new standards. So that's it for my part. Thank you for listening. Bye-bye.